she's been a student in the School of Computing since 2007. She started working with me in 2008. I then went on sabbatical. I brought her to a conference outside the U.S. in which she was stuck and not allowed to get back into the country for a year. I went into the hospital. I think she was the only student that was saddened to see me go in the hospital. I think she was thinking that she may have to switch advisors and start on a totally new topic. And in the midst of all of that, yet, as you will see, she had a very productive 4 years working with me. And it's been quite a pleasure to work with her, and I hope her the best in where she moves on to. So today she's going to present her work, which has been concerning smoothness-increasing, accuracy-conserving filtering applied to discontinuous Galerkin methods.
Well, thank you, Mike, for the introduction, and welcome everyone to my defense. So as Mike already mentioned, I'm going to talk about smoothness-increasing, accuracy-conserving filtering for discontinuous Galerkin solutions. And I'm sorry? Jennifer, can you hear me? Spencer, Jennifer? Yeah, I think this is supposed to be for Spencer and Jennifer. Can? Okay. Should I continue? Okay. So hopefully by the end of my presentation, you will have some idea of what these words mean. I will start off with a motivating example. Imagine that we have a velocity vector field, and we are interested in its streamlines. Streamlines are lines that are tangent to the velocity vector field. For example, here, if x represents my streamline and f is my velocity vector field, this equation basically says that the tangent to the streamline is equal to the value of the velocity vector field at any point. There are several time integrator schemes to solve this ordinary differential equation. For example, here I have the forward difference approximation of the derivative term. But so obviously, if we want to use a higher order time integrator, we can use more terms in the Taylor series expansion. But for that, we require certain levels of smoothness in our velocity vector field due to the derivative terms that we have in the Taylor series expansion. Normally, this function f is the result of some numerical approximation. And if it has discontinuities, we are not provided with the level of smoothness that we seek for our higher order time integrator. For example, in this example that I have here, I have the velocity, I have the vector field of some, the velocity field of some sample vector field. Here, the black line, the black streamlines, are streamlines that have been calculated using some higher order time integrator, using the analytical function, example function. The blue line represents the streamlines that have been calculated after using some approximation of our velocity field, velocity vector field that has discontinuities. And as you can see, these two lines, the blue and black, do not overlap all the time. However, after introducing smoothness back to our solution through some filtering technique, we get these red lines that overlap all the time. And it is this filtering technique that I'm going to talk about for the rest of this presentation. I will first talk about our model problem and the approximation scheme we use. So basically, to simulate any physical process, the starting point is a mathematical model. Here, we focus on conservation laws that are the principal mathematical model behind many physical processes. Let's say that we have this control volume V, and we are interested in the rate of change of some variable u that could, for example, represent energy, momentum, angular momentum, and etc. So we are interested in the rate of change of this variable within the volume V. And also, we denote the rate of change, the rate at which this variable leaves and enters the volume V through the boundary A with this term, and we call it the flux. So according to the principle behind derivation of the conservation law, the addition of the sum of these two terms should equal the rate of production of u within this volume that here I have denoted with S. so which is also referred to as sink or source. For example, chemical reactions, heating or cooling, will rise to this term. If we want this equation to be valid for any volume V, we can, so this is called the integral form of the conservation law. If we want it to be valid for any volume V, we get the derivative form of the conservation law, and here we have, for example, take advantage of the integrating by parts or Green's theorem to get the divergence set. In our work, we represent F to be VU, where V is a stationary velocity. And if I just plug this into my equation, I get this hyperbolic transport equation. And in hyperbolic equations, information travels forward in time and along the streamlines of this velocity field. And this is the type of equation that I will provide a lot of numerical examples for in the next slides. So to solve this equation numerically, we use the discontinuous Galerkin scheme. Here again, I have the transport equation for which the source term is 0. And let's say that I want to solve this in this two-dimensional field omega. What I do first is that I discretize this, I present a triangulation of this domain, and I denote my approximate solution with U sub h in each of these triangular elements k. And if I plug this into my main equation, I get this equation, and obviously this is not equal to 0, otherwise my approximate solution will be equal to my exact solution. In Galerkin schemes, we require this equation or the residual to be orthogonal to a set of test functions, and this orthogonality can be shown by this inner product here. And if I consider a polynomial approximation for my approximate solution, I can then plug this into this equation, and I'll end up with with a linear system that I can solve and then get the polynomial coefficients. In the discontinuous Galerkin scheme, these bases and test functions are the same, and they belong to the space of L2 integrable functions. In other words, they are allowed to have discontinuities between element interfaces. So as a result, my final approximate solution will have discontinuities at element interfaces. I don't know why this is messed up. Okay, so to finish our discontinuous Galerkin approach, I should mention that most often when we are solving these schemes, we are interested in the value of the solution at the element interfaces. And this is possible through the concept of numerical flux, which is a function of the left and right value at the element interface. I think the projector has messed up the figures a little, but it's okay. So this is supposed to be on the right side of the red line. So for example, and this numerical flux should be set in a way so that it mimics the flow of the information. For example, in this picture here, if my flow is going from left to right, one way to set the value at the interface is to take the immediate left value, and this is called the upwinding scheme. So why do we use the discontinuous Galerkin? Because it easily handles complex computational domains with higher order approximations. It has easy HP adaptivity because we can treat each element locally, and if we want to have a higher order approximation at some part of the domain, we can just do it easily within the element itself. It's very popular with the fluid flow calculations, partially due to the tricks we can do with the numerical flux. And also it is easily parallelizable, again, due to the fact that it treats each element locally. But as I said, so this will result in discontinuities in the solution, and it could lead to those potential problems I said earlier in this presentation in streamline visualization. So now we'll talk about filtering schemes for numerical solutions. First, a very brief history. I here only have mentioned the two most related previous works in filtering to our work. In 1977, Bramble and Schatz introduced filtering for finite element schemes applied to elliptic problems. many years later, in 2002, Cockburn, Luskin, Shu, and Sully, based on the work of Bramble and Shaz, introduced filtering for hyperbolic PDEs solved with a DG scheme, and this is exactly the type of equation we are working with in this talk. A lot of things happen here. You will find that in my dissertation. And I should also mention that there are also filtering techniques for finite difference and spectral methods based on similar concepts, but in this talk I only talk about filtering applied to DG solutions. So the filtering technique in one dimension is convolution with a kernel. So here U sub h is my final approximate solution, and this is my kernel. So if I just use the definition of the convolution, I will get the integral form. Here h represents the mesh characteristic, and basically it is used to scale the kernel, and it determines the extent of the kernel on the mesh. So this filtered solution will be much smoother comparing to the initial solution U sub h before the application of the filter. And the accuracy in the L2 and L infinity norms is preserved, and in many cases it is increased. In the field of visualization, this was introduced as a smoothness-increasing accuracy-conserving by Stephen Curtis, Ryan, and Kirby in 2007, and I will refer to this filtering technique as SIAC from now on. Kernel, our convolution kernel, is a linear combination of B-splines. Here, this represents a B-spline of order k plus 1, where k is the degree of our DG approximation, and these are the kernel coefficients. For example, I have the schematics of the kernel for k equal 1 and k equal 2, and if you notice, it has a symmetric form. We require our kernel to reproduce polynomials up to degree 2k. For example, if I consider monomials of degree 0 to 2k and convolve them with the kernel, I should get the same monomial back. And this provides a mechanism to compute the kernel coefficients. So this way we compute the kernel coefficients. As an example, I have the one-dimensional transport equation here. With this initial condition, and I collect the results after 2 periods in time. Here are the point-wise error values for 3 different mesh resolutions before the application of the filter, and here are the same results after the application of the filter. And as you can see, the filtering is successful in introducing smoothness back to our solution, and also the magnitude of the errors are lower. The current limitations of this technique is its lack of theoretical and computational extension to non-trivial mesh structures. Uniform quadrilateral meshes were mainly considered in the previous works, and also expensive core operators. As we will see later, it is possible that we get many numerical integrations, and numerical quadrature could be expensive, and in higher dimensions could become a bottleneck. So these 2 limitations will lead us to our thesis statement, which is addressing the above limitations in order to make this filtering technique more suitable for real-life engineering problems. Our contributions can be grouped into these 2 general categories. The first one is that we provide study of the impact of the numerical quadrature approximations on the convolution. We provide different approximation techniques along with their error estimates, and the goal of this study was to provide a mechanism for computing the convolution operator in a more efficient manner. And also, we provide extension of the SIAC filter to non-trivial mesh structures. We provide results for general triangulations and tetrahedral meshes. So I will explain each of these in more detail in the next slides. First, I'll talk about the impact of the numerical quadrature approximations on the convolution. Here again, I have the postprocessor formula in one dimension, and since K is a linear combination of B-splines, it will have compact support, so I can just rewrite this infinite integral as finite local sums over here I sub I represents a DG element that is covered by the kernel support. So in this schematic, this curved line is my kernel. This is my DG mesh. This is the point at which I want to compute the post-process solution. And here is what we refer to as the integration mesh. For example, if I want to evaluate this integral over this DG element, we see that here we have a breaking regularity. So to be able to evaluate that exactly to machine precision, we need to subdivide this interval into these two intervals over which there is no break-in regularity. But more complex mesh structures could result in more integration regions due to more subdivisions that we might have over each DG element. So an alternative approach would be to use quadrature approximation, and one way to do that is to ignore the kernel breaks. Well, the idea behind this is that we still have some level of continuity at these kernel breaks. So we are able to control the error by just increasing the number of quadrature points. So as a result, when evaluating this integral, I only have one integration region, which is the DG element itself. So the integration mesh and the DG mesh will be the same. Here I have an example using for doing filtering using the approximate quadrature approach. Here I have a vector field that has oscillating closed circles as streamlines. In this zoomed in picture, the black line represents the streamlines that have been calculated using the analytical function. The blue line are streamlines that have been calculated with the DG approximation, basically before the application of the filtering. The red one, the solid red line, is the streamline that have been calculated using the exact quadrature approach for our filtering operation. And the dashed line is the streamline that have been calculated using the approximate quadrature approach. So as you can see, this still provides enough accuracy comparing to the before the application of the filter, and it closely follows the exact quadrature filtering streamline. As another example, I have the error results of the transport equation, a two-dimensional transport equation, with this initial condition. I again collect the with over a quadrilateral element domain. I again collect the results after 2 periods in time. Here in this table, you will see the error, the L2, these are the L2, and these are the L infinity. Results for a K2 approximation over a uniform quadrilateral mesh before the application of the filter. In this table, I have the results after the application of the filter using the approximate quadrature approach. And as you can see, the errors are lower and the order of convergence is higher than before the application of the filter. Here are the results with the exact quadrature approach. So as you can see, these results in this table are comparable. The order of convergence in the exact approach are a little higher with the comparing to the approximate quadrature approach, but they are still comparable. So in conclusion, input mesh-based filtering provides benefits that is comparable to exact integration filtering. And as I said before, error can be controlled by increasing the number of quadrature points. And also in visualization of DG solutions, for example, in the streamline example that I provided, input mesh-based filtering provides convenient means for obtaining smooth solutions with controllable accuracy. The detail of the error estimates and also more examples can be found in this published journal article. Next, I'm going to talk about the extension and application of this filter for structured triangular elements as shown in this picture. So this is size H. These are supposed to overlap with these, but they don't. Okay. So I first talk a little about the mathematical foundations of our work. According to the principal theorem provided by Bramble and Schatz, after the application of the filter to our numerical approximation, the order of convergence, this represents the L2 norm, the order of convergence is of this order, 2k plus 1, k being a DG approximation, and h is the mesh characteristic. Comparing to the usual L2 norm that we would expect from a DG scheme, which is k plus 1, this increase in the accuracy is noticeable. Normally to provide proofs for this error estimate, to show that how we can, to basically show how we can derive such higher error estimates, we divide this term into these two terms by simply adding and subtracting this term. As I mentioned before, to show, so if we show that we have higher order accuracy on each of these terms, we can then show that we have higher order accuracy on this left-hand side term. To show this higher order accuracy for this first term, we use the kernel property that I mentioned before, that it needs to reproduce polynomials up to degree 2k. And by using a Taylor series, we can easily show this error estimate for the first term. For the second term, it was shown by Bramble and Schatz that this term can be bound by a term that looks like this. This term here reads as the negative order norm of the divided differences of the error. So I will explain what this means in the next slides. So now that we are here, at the end, if we show that this term is of higher order, then this will be of higher order, and then this will be of higher order. I already explained how this can be of higher order, so let's see how this can be shown. The negative order norm is the norm associated with the dual space. The dual space of a Hilbert space HL is denoted by H minus L, and hence the term negative. And the dual space is a space of, for example, if U belongs to this Hilbert space, the dual space is the space of all linear functionals, and a linear functional can be represented by this inner product here. And by definition, the norm associated with this dual space will have the following form. Another way to look at this norm is, for example, if we replace this, we can consider a very simplified domain, for example, minus pi to pi, then, and we can assign these phi functions to be the complex exponential function, and obviously this belongs to C infinity. And these functions provide a set of orthonormal bases for this L2 domain defined on this domain. If I consider this for my phi function, then this term represents a normalized Fourier coefficient, and the negative order norm will be the supremum of these coefficients. Back to our theorem, if I replace U with the divided differences of the error, my negative order norm will be this. So if this will be of higher order, this means that the supremum coefficient of the divided differences will decay faster in the negative order norm comparing to the natural L2 norm. Normally, to show the higher order accuracy in the negative order norm, we try to use the error estimates available for the original DG scheme. For example, if I represent my difference operator as the forward difference operator here, and it is enough to show higher order accuracy for the forward difference, because if we use a more accurate difference operator like the central differences, it should be at least as accurate as the forward difference. Using the forward difference operator, if this is my original DG mesh, we have translations of size h here, which h is the size of my DG element. So my translated mesh will have the following form. This is the mesh over which the difference operator will act upon. So if this mesh is uniform, meaning that these elements are equal, which is the same, which is the case in the structured triangular mesh, my translated mesh will be exactly the same as my original DG mesh, and this will allow us to use the already available error estimates for our original DG scheme. So that's the idea behind providing higher order proofs for this term. Here again I have the two-dimensional transport equation. I again collect the results for this initial condition and after 2 periods in time. On the left, I have the before post-processing results for a K2 approximation, L2 and L infinity. And on the right, I have the results after the application of the post-processor. As you can see, the magnitudes of the errors have decreased, and we were able to increase the order of convergence from K plus 1 to at least 2K plus 1. This is for K equal 2. Here I have the pointwise error plots. On the left, I have the results before the application of the filter, the 3-dimensional view of the pointwise errors. And this is the filled contour plots. And on the right, I have the results after the application of the filter. The results are much smoother as you can see, and the errors are smaller comparing to the before post-processing results. I have another example with the transport equation, but this time with a variable speed. So this is the speed that I use with the same initial condition. Again, the results after 2 periods in time. And we observe similar results to the transport equation with a constant speed. So the conclusion that we can make is that through the application of the SIAC filter, we are able to improve the order of accuracy from K plus 1 to better than 2K. And this is important because previously accuracy enhancement on triangles was only K plus 2. And as we saw, the filter field is much smoother. Again, the detail of the proof with more examples are available in this published journal article. Yes. Okay. Say that again. Mm-hmm. Yes, it could be a quantity that's defined for the members of the Hilbert space. Yeah. So here, we normally use this as a quantitative measure of the functions in L2. And I guess I didn't quite get your question. Okay. We are still acting in our original Hilbert space. It's not like we are moving to another space. I guess I didn't answer the question. Why is that your question? We get better accuracy in this norm because we can provide higher order estimates for this norm. And as this can be an upper, and we can show that this can be an upper bound on the L2 norm after filtering. Like for our filtered solution, this can be an upper bound. Yeah, but we can discuss later. Okay. Okay, so now I'm going to talk about the extension of the SIAC filter for more general triangulations, including what we call the translation invariant meshes, and also an example of adaptive mesh. So, as I showed before, to derive higher order estimates, we relied on the superconvergence in the divided differences. And for that, we try to stay in the same solution space as the original DG solution so that we can use the already available error estimates for DG. A more general type of meshes that will allow us to take advantage of this fact are called the translation invariant meshes. According to the definition provided by Babushka, a translation invariant mesh is a mesh that is formed by repeating some base tessellation of size h. For example, in this mesh, if this is my base tessellation and of size h, by repeating this, I get this mesh that is translation invariant, meaning that if I translate it with size h in each of these directions, I will get the same mesh back. Two more common types of translation invariant meshes in finite element domain are the Union Jack mesh and the chevron mesh. And in each of these, I have highlighted the base tessellation with in red. So using translation invariant meshes, we can now modify our main theorem like this, meaning that if I use now the translation invariant of the mesh to scale my kernel, I should be able to get higher order accuracy or to observe psi characteristics. Here, this is really messed up. So this is supposed to be here, and this is supposed to be here. Here I have the error results for various kernel scalings over the Union Jack mesh. I have the error results. So this axis represents different scalings, and this axis is the L2 norm. And these are these results are for 4 different mesh resolutions, with the black one being the finest mesh resolution. So as you can see, if I use a fine enough mesh, using a scaling equal to the translation invariant of the mesh, I get the minimal L2 error value. In the plot on the right, I have the field contour plots. This one is after the application of the filter, but not using the proper scaling. After using a scaling that is equal to the translation invariant of the mesh, as you can see, we get almost perfect smooth results. And we'll get similar results for the chevron mesh. I did not repeat the plots here. We went one step further, and we showed that it is also possible to observe psi characteristic for an adaptive mesh. For our adaptive mesh, it still has a base tessellation of size h, but now each of these base tessellations can have a different subdivision than the other. They are not required to have the same subdivision. So for this, here again the rectangle is supposed to be here. Again, as for a fine enough mesh, black being the finest, using a scaling equal to the translation invariant of the mesh, we will get the minimal L2 error value. On the right, I again have the contour plots not using the proper scaling. And as you can see, the results get much smoother when we apply the proper scaling. So with these results, we can say that through a proper kernel scaling, we are able to show mathematically and numerically psi characteristics for translation invariant and adaptive meshes. Again, more results with the details of the algorithms can be found in this accepted journal article. And finally, I'm going to talk about the extension of the SIAC filter for unstructured triangulation and structured tetrahedra. For unstructured meshes, there is no translation invariant property, and there is no inter-element relation as in the adaptive mesh case. But a natural question we could ask ourselves was that, will it work in practice anyway? To answer that question, here I have a Delaunay triangulation, and I have a similar set of plots as before for 4 different mesh resolutions. And these scalings are multiples of the largest element size of all the triangular elements in the domain. And for scalings around the largest element size, when the mesh is fine enough, we can get the minimal error value in the L2 norm. Here in this contour plot, I have the before post-processing results for a P3 approximation, and as you can see, it's really noisy. This is after the application of the SIAC filter using a scaling that will result in the minimal L2 error value. It is, as you notice, it is not as smooth as the results we had for structured triangulations, but we can always get more smoothness by increasing the polynomial order. Here I have similar results for a stretched triangulation, or this is a so-called anisotropic mesh, and it's often a type of mesh we would see when, for example, simulating flows that have a strong preferential direction. Again, for scaling around the size of the largest element side of all the triangular elements, we are able to observe minimal error value in the L2 norm. Here again, I have the plots, like filled contour plots for the error before the application of the side filter, after the application of the side filter, and I could increase the smoothness by using a higher order polynomial. We also tested our filtering scheme for these two other variants of the unstructured mesh that have obvious change in element sizing in the interior of the domain, and we observed similar results, and I did not repeat the plots here. So in conclusion, although the SIAC behavior cannot be mathematically proved for unstructured triangulations, in practice we are able to observe similar behavior by using a proper kernel scaling. And the detail of the algorithms are provided in this journal article that was recently accepted under revision. To show that adding another dimension will not affect the quality of the results, we tested our SIAC scheme for structured tetrahedral meshes. If the tetrahedralization is based on a structured hexahedral mesh, we should be able to observe SIAC characteristics. There are many eight different ways, exactly, to subdivide a hex element into tetrahedra. It doesn't matter which one of these we choose. We should be able to observe higher accuracy and more smoothness. Important point in implementation of SIAC filters for tetrahedral meshes is that we end up solving this sort of geometric intersection problem between a tetrahedral element and the kernel. And we are required to do that so that we can find these integration regions over which there is no breaking regularity. If we use the convenient tensor product quadrature rules, we'll end up getting a lot more quadrature points that are required, that are necessary, and the filtering scheme will essentially not be practical in this case. However, we could take advantage of more general quadrature rules that are rules based on barycentric coordinates. For example, in this table, I have a comparison between the number of points for these DG approximation. These are the number of points required when evaluating an integral in 3 dimensions in our filtering scheme. And as you can see with the quadrature rules, we will be using a lot less points than the tensor product rule. However, the problem with the quadrature rules is that to get these points, we often need to find the roots or minima of a multivariate polynomial, and they are very difficult to solve in general for higher order schemes. Like, we were not able to find the points for the P4 approximation. However, we observe in practice that we require a lot less points than these points predicted by the theory to observe SIAC characteristics. So with this number of points, I collected the results for the transport equation in 3 dimensions after 2 periods in time. These are the results for K2, for a K2 and K3 approximation. On the left, I have the results before the application of the filter, and on the right, after the application of the filter. You can see that the order of convergence has increased from K plus 1 to at least 2K plus 1, and the magnitudes of the errors have decreased. And to verify that we have indeed smoothness in our solution, I have an isosurface of the sample function here. We use a modified version of the marching cube in which we use a higher order root finding scheme to find the intersection point on the cube. And if I use that higher order root finding scheme, and this is my DG approximation, I'm able to observe the discontinuities in my solution. But as you can see, if instead of this, I use my post-process solution, the final results are much smooth, is indeed smooth, and this is not smooth. A very brief note on the performance of the post-processing. Jim provided the CUDA parallelization of this filtering technique, and we observed that we are able to get up to 18 times the speed up for triangular meshes when performed on one GPU comparing to a single core CPU implementation. And for quadrilateral meshes, we observed up to 50 times the speed up. And it's a perfect candidate for parallelization because, as you might have noticed by now, post-processing each point is totally independent of the other point. And we also observe perfect linear scaling using OpenMP parallelization. And the details of the algorithms are provided in this published journal article. What we provided could be grouped into these two categories. We provided efficient means to evaluate the convolution operator, and we provided extension to general tessellations. A potential future work could be the mathematical extension of the SIAC filter to unstructured tessellations. As I explained, right now we are not able to mathematically prove the SIAC characteristic on unstructured triangulations, and for that we probably need to focus on the estimates for the divided differences. Also, as I mentioned, the kernel that we use in our work has a symmetric shape, and which is not a suitable kernel to post-process near boundaries or shocks. So there are already versions of a one-sided filter that can be applied near boundaries or shocks, but they're not robust all the time. So as another future work, developing a robust one-sided filter and its application to streamlining. And also we still need to investigate the impact of post-processing of DG flows. For example, one parameter that we should look more carefully into is to see how post-processing would affect the metrics such as Hausdorff distance. At the end, I would like to thank Mike for his patience, support, and guidance through all these years. Jennifer for her continuous support, and also for kindly hosting me in the Netherlands for 2 consecutive summers. The rest of my committee members, Martin for helpful scientific conversations, Spencer for the amazing support of the Nectar++ library, and of course Chris for such an awesome atmosphere we have at SCI. And many friends have helped me stay sane all these years. I especially thank Vincent, Samar, and Puyan, and also many more. And last but not least, my parents, my brother, and my sister. I would also wish to acknowledge the funding provided for this work through Air Force Office of Scientific Research, Program Manager Dr. Fariba Fahru. Thank you.
All right, so now Spencer and Jennifer, if you want to participate in the public questions, you can turn on your mics. The procedure is that now there's public questions, so if any of you have questions, those can be asked. You're speechless.
So in the part of unstructured grids, you mentioned you have to have a proper scaling for your kernels. So how do you define that?
Well, there is no precise way to define that. By proper, I basically mean that if we perform a series of experiments in which we gradually increase the size of the kernel, there is a point that we observe the minimal error value, and normally we would expect that sort of intuitively, not analytically, maybe that this should be around the size of the largest element side. Because in the proofs we always assume that this mesh characteristic that is a representative of the largest element side in the domain. But
Are there any other public questions? Well, let's thank the speaker again. Okay, so now now will be the private part, so if the audience can part, feel free to grab snacks on the way out.
A lot